Okay, so now we're actually going to get into some counting. So here we start with an example, and this is going to be an example of something that we're going to call the multiplication principle. So we'll do many examples in this video. So suppose we would like to make a list of length 3, okay, such that the first entry is something from the set A, B, C. So the first entry is either A or B or C. That's the first entry of the list. The second entry of the list is either going to be 5 or 7. And the third entry of the list is either going to be A or X. Question: how many such lists can we make? We would like to count. We would like to count how many lists like this can we make following these rules. Okay, so the book has a whole method of doing this, which is just really good for the very first time you're learning about it. You should not have to do this whole method that I'm about to show you on every such problem, right? So what the book does is it draws a tree like this, and the idea is we start here on the left and we make a first choice, meaning what should we put in as the first entry of the list? We want to make a list of length 3, so the first entry has to be either A, B, or C. So we have 3 choices here for the first choice. Then for each of those 3 choices, we have 2 choices for the second entry. Or the second entry is either 5 or 7. And then for each of those options, we have 2 choices for the third choice. Two options for the third choice, either A or X. And then here are all the resulting possible lists on the right side here, right? So this is A5A, and then we have A5X, and then we have A7A, and then A7X, and then B5A, and B5X, and so on. So if we count up all these lists, we have 12. So the answer to the question is there are 12 such lists. Okay, so here's one way you can think about it. There are 3 choices for the first entry, 2 choices for the second entry, and 2 choices for the third entry. And the idea is that no matter what we choose in the first choice, we have 2 new choices for the second choice. So for each of these 3 options in the first choice, we have 2 options in the second choice. And for each of those 2 options in the second choice, we have 2 options in the third choice. So we have to multiply 3 times 2 times 2, which gives us 12. Let's do another example, similar example. Suppose we would like to make a list of length 4 from the letters of the set A, B, C, D, right? Okay, so we have these 4 letters, and we would like to make a list of length 4, where the list is not allowed to have a repeated letter. So this is a little confusing, perhaps. Generally, lists are allowed to have repeated letters. However, we can impose our own restrictions on a list. We can say, okay, I'm designing a list right now that should not have duplicates. Okay, it should not have repeated letters. But the general idea of a list, yes, repetition is allowed. But in this particular example, we're imposing a restriction on the list, and we're saying the list cannot have repeated letters. So the question is, so again, we have these 4 letters. We would like to make a list using those 4 letters without any repetition. How many such lists can we make? Okay, so here again, this is an introductory problem, so we can draw a tree. We don't actually need to draw the tree for most problems. So the idea is we have the first choice is either A, B, C, or D, right? So again, the first item in the list is either going to be the first entry. I should be consistent. The first entry is either A, B, C, or D. Okay, so those are our 4 options for the first choice. And then for the second entry of the list, it's either B, C, or D. For the third, scratch that. If I chose A as the first choice, I cannot repeat it. So which options do I have for the second choice? It's either B, C, or D. Now, similarly, if I chose B as my first choice, so I cannot repeat B. So for my second choice, I can either do A, C, or D. And similarly for the rest. So if you think about it, what you have here is you have 4 choices for the first for the first choice, you have four options. It could be A, B, C, or D. The first entry, you haven't used any letters yet, so you can choose any of the four letters. Now, whatever you chose as the first entry cannot be used again, right? Because we're not allowed to have repeated letters in this list, in this particular example. So whatever we chose for the first choice cannot be used again. So for the second choice, we have three options. And then whatever we chose for the second choice can also not be used again. So we have so for the third choice, we have two options, right? Because we've already used two of our letters, whatever they are, and we have two options left. And then for the fourth choice, we have just one option. We don't have any choice to make, really. It's kind of a misnomer. We don't really have much of a choice. We have to take the last remaining element, the last remaining element of the set, and use it as our fourth entry. So the idea is there are four choices for the first entry, three choices for the second entry, two choices for the third entry, and only one choice for the fourth entry. Thus, the total number of possible lists is 4 times 3 times 2 times 1, which is, well, this is not 12. This should be, this is 24. It's a mistake. All right, so 24. Okay, so these two previous examples were examples illustrating the multiplication principle. Okay, so here we stated as a fact, as a general fact. Suppose that in making a list of length n, there are a sub 1 possible choices for the first entry, a sub 2 choices for the second entry, a sub 3 possible choices for the third entry, and so on. Okay, so suppose that is true. Then the total number of different lists that can be made this way, right? The total number of lists that can be made following these restrictions is the product A1 times A2 times A3 times ... times A sub n. So the number of options for each entry multiplied all together. That's the total number of different lists that can be made. So for example, an everyday example, suppose that when ordering coffee, you have a choice of whole, skim, or soy milk. So you have three different options for milk: whole, skim, or soy. And then as for size, you have three options: small, medium, or large. And then for espresso, you have either 1 or 2 shots. How many choices do you have in ordering one drink? So you want to order a drink. How many total choices do you have? Like, how many different types of drinks can you order? So the answer is, so your choice can be modeled by a list of the form, milk type, size, number of shots, right? So it's a list of 3 entries. The first entry specifies the milk type, the second one specifies the size, and the third specifies the number of shots of the espresso. And there are 3 choices for the first entry. So that is our A1 in this example. And then A2 in this example would be 3 choices for the second entry, because you have 3 different sizes. And A3 in this example would be 2, which is the 1 or 2 shots of espresso. Those are 2 different options. So by the multiplication principle, the number of choices, the total number of choices is 3 times 3 times 2, or 18. Here's another example. So a standard New York State license plate consists of 3 letters followed by 4 digits. For example, JRB 4412 or MMX 8901. Those are 2 standard license plates. Now notice repetition is allowed. Going back to the previous example, in this example, repetition is not allowed, right? Like, the first entry has to be one of the 3 milk types. Can't be a different type of thing. The second entry has to be a size. It cannot be a milk type, right? So you cannot repeat things, because each entry is in this example right here, each entry is a different type of thing. So you cannot repeat things. But in a standard license plate, you can repeat letters, you can repeat digits. No worries about that. So question is, how many different standard New York State license plates are possible? And, so you can say, you can think about it like this: will, when the population, New York's population, will grow, presumably, over the next, coming years, and question is, will we run out of license plates anytime soon? So here's how to approach this. We can model a New York State license plate as a length 7 list, right? A list of length 7, where the first 3 entries are letters and the rest, meaning the last 4 entries, are digits. So now we can ask, how many such lists are possible? Like how many such lists can we make? Well, the first entry has to be a letter. So there are 26 possibilities for the first entry. I mean, in a license plate, there are only capital letters. So we don't have to worry about uppercase and lowercase. In some examples, you might have to worry about, do uppercase and lowercase, are those both possible? But here we don't have to worry about that. We're only dealing with capital letters, uppercase letters. So there are A1, meaning 26 possibilities for the first entry. So that's A1 in this example. Similarly, there are 26 possibilities for the third entry, so that's our A2. And then there are 26 possibilities for the third entry, so that would be our A sub 3. So those are the possibilities for each of the first 3 entries. For the fourth entry, there are 10 different possibilities, and that's our A4. A4 is 10 because it could be any digit, 0, 1, 0 through 9. Likewise, A sub 5 and A sub 6 and A sub 7 are all equal to 10, because again, for entry 5, 6, and 7, you can put any digit you want, and we don't have to worry about not repeating, because you're allowed to repeat digits. Even all digits can be repeated, right? You can have JRB 4444. That's fine. That's legal. It's a legal license plate. So, thus, the total number of such lists, right? The total number of these length 7 lists, where the first 3 entries are letters and the rest are digits. How many possibilities? What's the total number of such lists? Well, it's going to be A1 times A2 all the way times A7, right? A1 times A2 times A3 times A4 times A5 times A6 times A7. Now, this is really going to also give us the total number of possible standard New York State license plates, because we are using these lists to model standard New York State license plates. These should be equivalent values. So this is 26 times 26 times 26 times 10 times 10 times 10 times 10, which is this, 175,760,000. This is quite a large number, so we don't have to, I don't think there are anywhere near this number of vehicles with New York State license plates at the moment. Okay, so that's a nice example. Next, we're going to have a counting example involving lists of length 4 made with these symbols, A, B, C, D, E, F, and G. And just to clarify, we obviously do not have to use all these symbols in the list, right? What we're saying is, I want to make a list of length 4, or I want to consider lists of length 4 made out of these symbols, but I don't have to use all the symbols. I don't, right? Because anyways, this is just, when I'm making these lists, I'm using these 7 different symbols, A, B, C, D, E, F, and G. Okay, so we're going to have, this example is going to have 5 different parts, and they're going to illustrate a lot of important ideas in counting. Okay, so part A, there's going to be parts A through E. So part A is, how many such lists are possible if repetition is allowed? So that's the most basic question, I suppose. So again, I want to make a list of length 4 using any of these 7 symbols, and repetition is allowed in part A. Okay, so the solution is, here, this is a pretty standard way of approaching a counting problem. Consider the number of choices that we have for each entry. So we'll draw a list and leave it blank, and draw lines to indicate, there are some items going here. There are some entries in the list, and this particular list is going to have 4 entries. And what we're going to do is consider how many choices do we have for each entry. And then we'll multiply those numbers together, and that will give us our answer. So question is, how many choices do we have for this first entry here on the left? Well, it could be A, B, C, D, E, F, or G. So there are 7 choices there. So we have 7 choices. Now we don't know what it's going to be, right? We don't know. It could be any of these 7, but we know we have 7 choices here. Next, how many choices do we have for this entry? Well, we have 7 choices again, because we're allowed to repeat. We're allowed to repeat letters. Right? Repetition is allowed in part A. So we can, no matter what we use in the first entry, we can use any of these 7 letters in the second entry. So once again, we have 7 choices. And then for the third entry, we also have 7 choices. And then for the fourth entry, we also have 7 choices. So now by the multiplication principle, the total number of lists that can be made this way is 7 times 7 times 7 times 7, which is 2,401. Okay. That was fairly straightforward. Part B, how many such lists are possible if repetition is not allowed? So once again, we consider the number of choices that we have for each entry. So the first entry on the left, how many choices? We have 7. It could be A, B, C, D, E, F, or G. Now, how many choices do we have for the next entry? Well, whatever we used here in the first entry, we don't know what it is, but whatever we used, we cannot repeat it. So we only have 6 choices for the second entry. For the third entry, we cannot repeat anything that we picked for the first entry, and we cannot repeat whatever we picked for the second entry. So we have only 5 choices here. And then for the last entry, we cannot repeat whatever we chose here. We cannot repeat whatever we chose here. We cannot repeat whatever we chose here. So we only have 4 options left. So we have 4 choices for the last entry. So by the multiplication principle, the total number of lists that can be made this way is 7 times 6 times 5 times 4, or 840. Part C. So again, the same setup, list of length 4 made with these 7 symbols. So part C, how many such lists are possible if repetition is not allowed and the list must contain an E? So here we're putting an additional constraint. The list has to contain an E. Somewhere in the list there has to be an E. Okay, so this is again going to be trickier. Because the problem is we don't know where that E is. If we would know that the E has to be at the beginning, let's say, then it would not be any more difficult than the earlier problems. But we don't know where the E is. It has to be somewhere in the list. So here's how we do this. So we know that E must occur exactly once in every list. Now, think about this. How do we know it has to occur exactly once? Why can't it, right? All we were told in the question is that the list must contain an E. But how do we know that it cannot contain more than one E? Like, how do I know that E must occur exactly once? How do I know the word exactly? And you have to be very precise in math. So how do I know this word? Where do I know this word from? Okay, so this is coming from the fact that repetition is not allowed. All right, so if I know I need to have E, and I cannot repeat any letter, that means I cannot repeat E either. So that means in each list, there has to be the letter E, and it has to be there exactly once, not more than once. Okay, great. Okay, so E must occur exactly once in every list. Furthermore, so if we think about this, E is either the first entry, the second entry, the third entry, or the fourth entry. But it's one of those 4 choices, right? It's one of those 4 things. So what we're going to do now is divide the possible lists into 4 non-overlapping categories. So we have various many different types of lists that we can make to satisfy the condition of the question. Again, what's the goal here? We are given some conditions and we want to know how many lists can we make to satisfy this condition, these conditions. So what we're going to do is take all these possible lists that can be created and divide them up into 4 categories. And these are going to be non-overlapping categories. So here they are. So category 1 has the E as the very first letter. And then the other, letters we're not sure yet what they're going to be. The other entries we're not sure yet. Category 2 has E as the second letter, the second entry, and we're still not sure about the others. Category 3 has E as the third entry, and category 4 has E as the fourth entry. Okay, so these are 4 categories, and they're non-overlapping because if you think about it, if you have, for example, if you have E as the first entry, you cannot have E as the fourth entry, right? So you cannot be in, let's say, category 1 and category 4 at the same time, because we know that E must occur exactly once in every list. Okay, so now we go through each of these categories one by one and figure out how many choices we have for all the unknown entries. So for this one, how many choices do we have? Well, we used E already, and we cannot repeat letters in this part of the, in part C. Repetition is not allowed. So we have 6 choices, right? We cannot use E again, but any of the other letters are fair game. For the next entry in category 1, we cannot reuse E, and we cannot reuse whatever we used here. So we have 5 choices, and then we have 4 choices for the next one. Going to category 2, for the first entry, we have 6 choices, and then 5, and then 4. And going to category 3, we have 6 choices, 5 choices, and 4 choices. And category 4, 6 for the first entry, 5 for the second entry, 4 for the third entry. Okay, now these 4 categories divide up all the possible lists that we're looking for. All right, we're looking to count how many possible lists are there where repetition is not allowed and the list must contain an E. So these 4 categories encompass all those possibilities, and they divide up all those possibilities. So what we can do is figure out how many lists are in each category and add up those results. So how many lists are there in category 1? Okay, so this is just a basic multiplication problem, multiplication principle problem, right? How many entries, how many lists are there in category 1? Well, we have 6 choices here, 5 choices here, 4 choices here. So we have a total of 6 times 5 times 4 choices for category 1. Now you might say, what about E? Well, E, for this entry here, I have 1 choice. So just multiply it by 1, which doesn't change anything. So the total number of lists that can be made this way is, well, for the first category, we have 6 times 5 times 4 lists that can be made this way. Category 2, also 6 times 5 times 4. Category 3 also, category 4 also. And now we add them up because these 4 categories encompass all possible lists that we're looking for. So we can just add up the categories. So this is going to be 120 plus 120 plus 120 plus 120, or 480. Okay, we're going to come back to this example in the next section where we're going to formalize this idea. This is known as the union rule, but for now we're just thinking about them as categories. Next part of the example. So again, we're talking about lists of length 4 made with the symbols A, B, C, D, E, F, and G. And then the question is, I should have put in a pause here, but okay. Meaning I should have broken up the slide, but okay. The question is, how many such lists are possible if repetition is allowed, okay, and the list must contain an E? So it's very similar to the previous one, but except that in the previous one, repetition is not allowed and the list must contain an E, and here repetition is allowed and the list must contain an E. Okay, so solution. From part A, we know that the total number of length 4 lists with repetition allowed is 2,401. That was part A, right? How many lists of length 4 with repetition allowed are possible? Answer was 2,401. Now that's not the answer to this question, right? So what we're going to do now is, in order to figure out how many of these 2,401 lists contain an E, which is what we're looking for. We're looking for lists that allow repetition, but the list must contain an E. So in order to figure out how many of these lists from part A contain an E, we will subtract from 2,401 the number of lists that do not contain an E, right? If I have these 2,401 lists, some of them contain an E, some of them don't contain an E. I want to know how many of these lists contain an E. Well, one way to do that, one way to figure it out is to subtract all the lists that do not contain an E. And whatever I'm left with will be the number of lists that do contain an E. So now, how many lists are there that do not contain an E? So if I want to make a list that does not contain an E, we have 6 choices for each entry. Right? Again, repetition is allowed in this example. So if I would imagine where there's no E, again, no E, so we have 6 choices for each entry because I can use A, B, C, D, F, or G, but not E. So there are 6 to the power of 4, or 1,296 lists without an E. So the answer to our question is that there are 2,401 minus 1,296, which is 1,105. This is the number of lists with repetition allowed that contain at least one E. Okay, so this was a little bit of a, well, we've never seen anything like this before. We're going to come back to this idea again in the next section, and we're going to see this is an example of what the book calls the subtraction principle. But now I want to, you may be wondering, can we answer part D in a similar way as we answered part C? Meaning, can we break this up into 4 categories just like we did in part C? So here's the potential pitfall. Okay, so I'm already alerting you that this is not going to work. Okay, but could we have solved part D like this? E must occur in every list. It is the first, second, third, or fourth entry. Let us divide the possible lists into 4 categories. We have category 1, where E is the first, category 2, category 3, category 4, and now we fill in the number of choices. Now here, again, in this, we're dealing in part D where repetition is allowed. So how many choices do I have for this entry? Well, I don't care if I used E already, I'm allowed to repeat it. So I have 7 choices here, 7 choices, 7 choices, and the same for all of them because repetition is allowed. So now, thus the total number of lists that can be made this way is 7 times 7 times 7 for the first category, plus 7 times 7 times 7, and so on, which should come out to 1,327. Okay, this is the wrong answer. This answer is wrong. The correct answer, as we found earlier, is 1,105, which is not the same as what we got over here. So one of these answers is incorrect, right? They cannot both be true because again, we're solving an objective question. How many lists are possible that satisfy these restrictions or these these conditions? So there has to be one answer, right? There can't be 2 answers. So I'm telling you that the correct answer was the one we got earlier, and that this answer that is on this slide is incorrect. But why? Why is this incorrect? Where did we go wrong here? It seemed like we had a good argument, right? We know that E must occur in every list. It could be the first, it could be the second, it could be the third or the fourth entry. So we divide the list up into 4 categories, and so where do we go wrong here? Okay, so here the problem is as follows: overcounting. That's the problem. The problem with breaking part D into categories and then adding up their sizes, which is what we just tried to do. The problem is that there is overlap among the categories, right? In part D, if we try to make these categories, there's going to end up being overlap among the categories. If you go back to part C, you'll see that I mentioned there that the categories are non-overlapping. So that was okay. But in part D, the categories do overlap, and I'll show you examples of that. So adding them up, if we would divide them up into categories and add up their sizes, there would be overlap among the categories, which would cause us to overcount the possible lists, right? Because again, the problem is if there's overlap among the categories, and then I count each category separately and add them up, but I'm going to be counting some things twice or even 3 times or even 4 times, because there might be some things that are in more than one category, which I'm going to end up counting more than once. For example, okay, here's missing a parenthesis, EEAB. Again, imagine there's a parenthesis here, closing parenthesis. EEAB, this is a list. It's part of category 1 because there's an E at the beginning in the first entry, and it's also part of category 2 because there's an E in the second entry. So according to the pitfall that we might have done incorrectly, what we'd have done is it's part of category 1 and 2, so it would get counted twice incorrectly. Similarly, this list, EECE, is part of categories 1, 2, and 4, so it would get counted 3 times incorrectly, etc. So there you can come up yourself with other examples of lists that would be part of multiple categories and therefore would end up getting counted multiple times incorrectly. So the point is, when doing counting problems, we must make sure that we aren't overcounting. Okay, continuing with this counting example, so we did parts A through D. Now we have part E to finish. So consider, again, we're talking about lists of length 4 made with these symbols A, B, C, D, E, F, and G. So part E says, suppose that the first entry must be either B, C, or D, and the last entry must be a vowel. Okay, so we have, again, 4 entries. First one has to be either B, C, or D. The last entry must be a vowel. So in this case, we have only 2 vowels to choose from, A and E. So question, how many such lists are possible? So once again, we'll consider the number of choices that we have for each entry. Okay, so how many choices do we have for each entry? Well, for the first entry, we know it has to be either B, C, or D, so we have 3 choices. How many choices do we have for the second entry? Well, we have 7 letters. We used one of them for the first entry, so it would seem that we have 6 choices left for the second entry. And then for the third entry, we have 5 choices because we already used up 2 of the letters and we cannot repeat. Oh, I'm sorry, I was not clear here. The question should state clearly that repetition is not allowed. Okay, so fix up the question. So suppose that repetition is not allowed. The first entry must be either a B, C, or D, and the last entry must be a vowel. So again, consider the number of choices we have for each entry. So for the first entry, it has to be B, C, or D, so we have 3 choices. Second entry, it would seem we have 6 choices because it could be anything except for what we chose for the first entry. And the next entry should have 5 choices. But now the problem is, how many choices do I have for the last entry? Well, it has to be a vowel. So you might say, well, okay, I have 2 choices, A or E. However, it's possible that I already used A or E in one of the middle entries. Right? It's possible that this entry here is A, or maybe this entry is E, or maybe this entry is A, or maybe this entry is E. So maybe there's only one possible option left. Maybe there's only one choice left for the last entry. There's no way to know. I don't know how many choices. So this is not a good approach. So let's try this again. So the idea is as follows. We have 3 choices for the first entry. Now we're going to go to the last entry, and we know how many choices do we have for the last entry. Well, we so far only used B, C, or D. So we have A and E left, and the last entry has to be a vowel. So we have 2 choices for the last entry. Now we can go back and fill in the middle entries. So we already used 2 letters, one for the first entry and one for the last entry. So for the second entry, we have 5 letters left. So we have 5 choices, and then 4 choices for the next one. So by the multiplication principle, there are 3 times 5 times 4 times 2, which is 360 such lists. Okay, so here's a tip. When you're doing such a type of problem, if some entries have restrictions, fill those in first. Fill those entries in first. So in this example, the first entry had a special restriction and the last entry had a special restriction. So we should fill them in first, and that will be helpful. Otherwise, we'll get stuck.